Hey guys, welcome to lecture 7 of digital signal processing lecture series. So in this lecture we will discuss about some of the questions or some of the problems of related to Fourier transform, and we will try to solve them. So basically we will tackle with these problems which I have listed here, mainly rectangular function, complex exponential, unit step function, and also these two. Okay, so without any further delay, let's start. Okay, so the first problem is on a rectangular wave where xn can be written like this. It is 1 when n is from 0 to an integer m, otherwise it's 0. So if we plot it, it will look something like this. The magnitude is 1, this is 0, 1, 2 m, otherwise it's 0. Okay, this is my xn. Fine. So the basic formula of Fourier transform is, we are already familiar with this formula. So to calculate the Fourier transform, we just have to put the value of xn. So if we put the value of xn, so it will be 1 into e to the power minus j omega n, and in that case the range of n will be from 0 to capital M, otherwise it will be 0 plus some 0 numbers. Okay, so this is nothing but a geometric progression or a GP series. So its summation, we can write it like 1 minus e to the power minus j omega m plus 1 divided by 1 minus e to the power minus j omega, the basic formula of sum of a geometric progression. Okay, so it can be written like, we take this factor common from the numerator and e to the power minus j omega by 2 we will take common from the denominator. Okay, so let's assume that if we like multiply 2j in numerator and denominator, so basically this portion is nothing but an expression of sinusoidal function, similarly 2j and the denominator. Okay, so this can be written like e to the power minus j omega m by 2 sine of omega m plus 1 by 2 divided by sine of omega by 2. Okay, so I'll just write it that we have used the property here, sine of theta is equals to e to the power j theta minus e to the power minus j theta by 2j. This formula we have used. This is the basic formula. Okay, and so fine. In that case, this is our final answer. Okay, fine. So now let's move forward to the second problem. So second problem is xn equals to 1 upon 2 1 minus cos 2 pi n by m if it is 0 to m or otherwise. Okay, so basic formula of Fourier transform is same as we have seen earlier. X of e j omega equals to summation n equals to minus infinity to plus infinity xn e to the power minus j omega n. Okay, yeah, to solve this problem, basically let's break this, first of all let's break cosine into e to the power j thetas. Okay, so we can write this in this form also, to the power j 2 pi n by m plus e to the power j minus j 2 pi n by m by 2, this is 0, and 0 to m 0. Fine. So here we have used the property that cos of theta is equals to e to the j theta plus e to the minus j theta by 2. Okay, fine. So now if we look on this term, so this term we can break in 3 parts. So let's call them a, b and c. So a is nothing but 1 upon 2, b is 1 upon 2 into e to the power j 2 pi n by m by 2. So I'll just change it to 1 upon 4, and c is 1 upon 4 into e to the minus j 2 by n by m. Okay, fine. So if you recognize this, this is just an extension of the rectangular function. Fine. Okay, so if we kind of extend this, this is nothing but 1 upon 2 minus 1 upon 4 e to the j 2 pi n by m minus 1 upon 4 e to the minus j 2 pi n by n m, when n is 0 to m, 0 otherwise. Okay, so this is just an extension of the rectangular function, or basically it is a summation. This is a rectangular function, we recognize. A is a rectangular function, b is a rectangular function multiplied by some phase, c is a rectangular function multiplied by some phase. Okay, so actually we should write it as a n, b n, c n. Okay, so in this case, so we have learned that if xn is equals to an plus bn, then x of e j omega will be, I'll write like xn is equals to an minus bn minus cn. In that case, this will be minus c e j omega. Okay, so a of e j omega we have already calculated in the previous problem, except the difference that there we calculated when it was 1, now when it is half. So it will be nothing but half into e to the power minus j omega m by 2 sine okay. Now b of e j omega. Okay, so to calculate the b of j omega, we know that there is a property that we have learnt in the previous lecture, that if Fourier transform of xn is x e j omega, then Fourier transform of xn into e to the j omega naught n is what? X of e j omega minus omega naught. Okay, so b of e j omega is 1 upon 4 multiplied by this exponential, or basically a phase vector. So it will be 1 upon 4 multiplied by phase shifted version of a rectangular function. Okay, which I am writing like minus 2 pi by m. Okay, because the phase factor here is 2 pi by m, or sorry, the omega naught here is plus 2 pi by n m. Okay, omega minus 2 pi by m m plus 1 by 2 divided by sine omega minus 2 pi by m by 2. Okay. Similarly, c of eg omega will be the only difference in b of eg omega and c of eg omega is the difference in omega naught. Here it is plus 2 pi by m. In the case of c eg omega or cn, it is minus 2 pi by m. Okay, so we can write it like plus 2 pi by m by 2 sine omega plus 2 pi by m plus 1 by 2 divided by sine omega plus 2 pi by m by 2. Fine. And x of eg omega we can calculate like this, where we have already calculated a of eg omega, b of eg omega and c of eg omega. Okay. Fine. Okay. Now problem number 3. In this problem, instead of given an expression for xn, basically they draw the samples of xn in discrete domain. Okay, so as we know that every sequence xn can be written as a summation of scaled and delayed impulse function. So this xn can be written like twice of delta n plus delta n minus 1, which will corresponds to this, plus 3 times delta n minus 3, which corresponds to this, plus 2 times delta n minus 4, which corresponds to this, plus delta n plus 1, which corresponds to sample at minus 1, minus delta n plus 3, which corresponds to sample at minus 3. Okay, so here we will use the property that if xn Fourier transform is x of eg omega, and if there is a time shift in the sequence, then there is a phase shift in the Fourier transform. Okay, fine. So x of e j omega can be written like Fourier transform of delta n is 1, then this will be e to the minus j omega plus 3 into e to the minus j 3 omega plus 2 into e to the minus j 4 omega plus e to the minus to the plus j omega corresponds to this, minus e to the j 3 omega. Okay, so this is a very simple problem. Fine. Okay, so now problem number 4, complex exponential. Xn equals to e to the j omega naught n. Okay, so let's say that in that case, from the Fourier transform pairs, we know that the Fourier transform of a complex exponential is given by this expression. Okay, okay, so instead of going this way, we will go in the inverse way. So if we prove that if the inverse Fourier transform of this is complex exponential, then this solves our problem. Okay, so the inverse Fourier transform is minus pi to pi 2 pi delta omega minus omega naught e to the j omega n. Okay, so here you noticed that we have taken only one instance or one period of the impulse function. As we know that Fourier transform is periodic in the frequency domain, okay, and the integration limits are over one period, that is from minus pi to plus pi. So that's why we have taken only single period of delta omega here. Okay, so this will be 2 pi cancels here. Okay, fine. So here the properties of impulse function comes very handy. Okay, which are like x of e j omega into delta omega is equals to 0, e of j 0 delta omega. So basically this shifts to the frequency where delta omega is. Area of delta omega over the frequency domain is 1. So these two properties are coming very handy here. So we have basically delta omega is located at frequency omega naught, so complex exponential basically shifted there, and as this is not a function of omega anymore, so we can bring out outside the integration. Then in that case the this will be integration minus pi to pi delta omega d omega, and this is 1 here. Okay, so this is the solution of this problem. Okay, so the next problem is interesting. Fourier transform of unit step function. Okay, so basically unit step function is neither absolutely summable nor it's square summable. Okay, so the basic so the expression of Fourier transform x of e j omega equals summation over n x n e to the minus j omega n, this will not converge. We have studied this in earlier lectures. If not, please go to the earlier lectures and understand this concept. So basically we will not go by this approach. Okay, so another way of calculating the answer, another way of calculating this is, let's assume that xn equals to the summation of two sequences where an is 1 upon 2 and bn is 1 upon 2 signum n. Okay, so let's draw them here. So 1 upon 2 for every value of n will look something like this. Okay, this is 1 upon 2, and 1 upon 2 signum of n. For positive value for n greater than or equal to 0, it is plus half, and for n less than 0, negative values of n, it is minus half, plus half, minus half. This is signum n into 1 by 2. This is n, this is n. Okay, so if we add these two, for negative values of n, plus half and minus half will cancel each other, so it will be 0. And for positive value or non-negative values of n, this will be half plus half, that is 1. Okay, this is 1, and this is what un is. Okay, fine. So let's write this bn. If we do bn minus 1, okay, so this is our bn is, Okay, so if we look closely that Bn is this, I'll draw Bn minus 1 also. Bn minus 1 means right shift this sequence by index 1. Okay, so first instance of plus half will shift to 1 and so on. And this is there is a minus half at minus 1 which will shift to 0 now, and it will be like this. This is 0, minus 1, minus 2 and so on. So this is our minus half, this is plus half. Okay, this is our Bn minus 1. So if we subtract these two, for n which are not equal to 0, we can see that it is for positive values of n, this is half minus half. For positive values of n, this is half minus half. For negative values of n, this is minus half minus half. That is that means that for non-zero values of n, this is 0, and for n equals to 0, this is half minus minus half. That means it is 1. So this sequence Bn minus 1 is 0 for all values of n except 0, and it is 1 only for n equals to 0. So it will look something like this, otherwise it's 0. So basically it is nothing but delta of n. Okay. So if we take the Fourier transform of this, it will be minus, and as we have already seen, if we are shifting in time, we are giving a phase in frequency equals to 1. Take B of E j omega common, only 1 minus. Okay, and regarding A of E j omega, we have already seen that Fourier transform of a constant is Fourier transform of 1 is 2 pi summation over k okay, where k varies from minus infinity to plus infinity. So basically A of j omega is pi summation over k delta omega plus 2 pi k. Okay, and finally we can write x of E j omega equals to A of E j omega plus B of E j omega. Okay, so A of E j omega is pi times summation over k okay, B of E j omega is 1 upon 1 minus e to the minus j omega. So this is the Fourier transform of unit step function. Okay, fine. So the next problem is x of E j omega is equals to 1 minus a square upon 1 minus a to the minus E j omega. Okay, and we have to find xn here. Okay, so let's break this fraction into sum of two fractions, and it can be written like 1 upon 1 minus a times e minus j omega plus a times e j omega upon 1 minus a times e j omega. You can solve this and finally you will get this. Okay, so Fourier transform of this, we have already calculated some Fourier or inverse Fourier transform of this, we have already calculated like this, and you can find in the Fourier transform pair also is a of n un. Okay, and regarding this, Fourier transform of e to the j omega is equals upon 1 minus a to the plus e j omega is a to the power minus n minus 1 u of minus n minus 1. Basically, I will leave it to you to calculate the Fourier transform of this. You will get this. Okay, so in that way the inverse Fourier transform of this expression will be this. Now if we multiply a on both sides, this will be a to the power minus n u of minus n minus 1. Okay, so this plus this, if we so the final expression of xn is a to the power n un plus a to the power minus n u minus n minus 1. Okay, so this is nothing but a to the power mod n. Okay, so this is the next problem. This is an interesting problem. So basically here we will use Parseval's theorem. And if we look in our discrete time sequences, we know that Fourier transform of a sinc function is a rectangular function in frequency domain. Okay, and here we notice that these are two different sinc functions. Okay, so if we want to draw their respective Fourier transform, we have to determine omega c. Okay, so omega c for the first sequence pi by 4n is this, omega c is pi by 4, and if I write this, this has omega c of pi by 6. Okay, so if I draw, it will be more clear if I when I draw their plots in frequency domain. So basically this sinc is of magnitude 1 by 2. So basically I can write it like, write both of them like 1 upon 2 times a sinc function with omega c equals to pi by 4, and this is 1 upon 5 times a sinc function with omega c pi by 6. Okay, so this is how they will look. Okay, this is minus pi by 4 plus pi by 4, and this is 1 upon 2. Okay, so and this I will say, okay, let's name them. Let's name x of n as this and y of n this, and this is and as this is a real sequence, so y star of n, or the complex conjugate of yn is basically same as yn. Okay, so this is xn, this is yn. So basically I am drawing x of e j omega. So this is x of e j omega, and yeah, this is minus pi by 6, this is plus pi by 6, this is 1 by 5. Okay, the y-axis scale seems to be reversed, so yeah, don't mind on that. So, and this is y of e j omega. Okay, this is yn, this is y of e j omega. Fine. So after that we have to calculate their multiplication. So if we multiply both of them, the final sequence will be like this: minus pi by 6 to plus pi by 6, and this will be 1 upon 6, sorry, 1 upon 10, 1 upon 5 into 1 upon 2. So this is x of e j omega into y star of e j omega. Okay, so the final equation, which is this, will be 1 upon 2 pi minus pi to basically minus pi by 6 to pi by 6, because this is non-zero over from minus pi by 6 to pi by 6, and its magnitude x into y star is 1 upon 10 d omega. Okay, so this is 1 by 2 pi into 1 by 10 into 2 pi by 6. 2 by 2 by cancel, and the final answer is 1 upon 60. So that's how we calculate it. Okay.